right, let's do it. There was a little quiet there, so that must be time. All right, here's the plan for today. Just to recap, we did a couple lectures on dynamic programming, right? So if you think about, kind of bird's eye view, what did we talk about in dynamic programming? We kind of talked about two limits where we know a lot about dynamic programming. Okay, so in one limit, people often call the tabular case. That's where everything is discrete. And then dynamic programming really is a lot like graph search, right? It's a form of graph search. Markov decision process is kind of the generalization of that. Okay, and in those cases, we have algorithms that just converge beautifully. We understand everything about their convergence properties and the like. So that's one of the cases that we understand very well. The other one that we talked about that we understand very well, I'll call it linear dynamics plus convex objective, which the LQR was the headliner there. That's the only one we really talked about. But more generally, there's a lot of things that you can do with a linear system. Okay, and so this is a very different set of systems. Like we can take a linear dynamical system in very high dimensions that would be extremely hard to make a tabular approximation of, but we can solve it perfectly. Right? Now, unfortunately, the things we care about the most are not tabular nor linear. Okay, but these are like footholds that we have to understand. So, actually, maybe a few of you came to, I gave a seminar last Friday. A few of you came, that was awesome. I talked about this thing called graph of convex sets, which I'm excited about. We'll maybe cover a little bit of it later. But one of the things that I like about graph of convex sets is, for those of you that went, is that you can imagine it sort of walks between the two worlds of graphs and linear dynamical systems and can bring together a new piece that we can think about very rigorously that sort of spans those two axes. Anyways, that'll make more sense if you didn't go to the seminar. That'll make more sense later. So what's my goal for today? My goal, we're talking about acrobots, cart poles, quadrotors. So basically, I want to use these tools. I want to study these tools in the context of a few specific canonical underactuated systems. And we're going to make them work, of course. We're going to make them not fall down. But we're also going to try to use them as an exercise to dig a little deeper into understanding what's happening in this machinery. Okay. Okay, a quick aside. So I always read the surveys. Thank you for your feedback. I always try to make things better. So please write everything you can and that you care about in those surveys. I really do take that seriously. I was like, a handful of people said, like, I just don't get diagrams. Like, why should I care about this? Like, they're annoying. They make the syntax worse. Why do I care about diagrams? So let me just take 2 minutes to say why you should care about diagrams, and then we'll move on. The funny thing that happens every single time I teach this, right? When at the beginning of the semester, people are like, I'm not trying to take a class on Drake. I don't really care about Drake, But then at the end of the class, they're like, why didn't you tell us more about Drake? Like, I could have done so many more things on my project if you had just spent a little time telling us about Drake at the beginning. So I always have to walk that line and, try not to bore you at the beginning, but it will make you powerful if you can master it. So, right, so we've already talked a little bit about diagrams, right? So my simplest possible diagram is just putting a controller onto my plant. And we have a dynamics engine in Drake, for instance, that will simulate a lot of the equations of motion of physical systems, acrobots, cart poles, quadrotors, you name it. Okay, so, but that alone isn't kind of enough to motivate like why you should care about diagrams and actually have to do copy to vector and a couple of things that make the syntax a little bit more gross, but more general, right? The thing is, if you start modeling complex systems, let's say Atlas, or any manipulation system or whatever, there's a lot more to just F equals ma inside the plant, right? Of course, there's the equations of motion, but there's also actuator models. There's sensor models. There's renderers that are one of your sensor models, right? There's a lot of things going on. And so, inside here, this sort of environment model, you're going to find compositions of systems that are built into diagrams that can model much more complicated systems than you would be able to model pencil and paper, or even if you just had to think about only a simulator that did physics. I always think about, so like Amazon Robotics uses Drake, and they have written some articles about it. And one of the things Andy, who leads that project, says is, he says, we actually started using Drake because of the dynamics engine. We thought it was a good dynamics engine. But he said it's actually the systems framework that is the reason they're using it going forward. Because if you can imagine, try to build a production system around big complicated robots, to be able to factor out and say, let's make an RFID model, let's make a whatever model, and you build up this huge amount of complexity around modeling your entire warehouse operations. That is described most naturally, I think. This is not a new Drake thing. This is a Simulink thing, Modelica. There's, throughout history, the way people have architected very complicated diagrams or complex systems is with the language of diagrams, block diagrams, right? This is like the same way object-oriented programming is very natural for some expressions, for some types of programming, functional programming for others. For dynamical systems, the block diagram, signals and systems abstraction has the one that is classically made that scale and work, where each little system can be written independently. It has input-output ports. It declares its state. That's how you build complicated dynamics equations. Okay, so it does. The great thing about the thing that's most unique about Drake is that even when you compose different dynamical systems together, like I always talk about, right, and we'll talk about it again today, the plant is not just a black box. It's got the manipulator equations inside it. They have certain structure. The mass matrix is positive definite, all these things. Okay. Let's say you're going to use the physics engine, but you want to put in some aerodynamic forces, or like a propeller or a wing or something like this. Okay? These all have certain structures. Drake tries to really continue to exploit the structure at the diagram level. So if you put a bunch of systems together and they're all linear, then you can still operate on the diagram like it's a linear system and use stronger optimization against it. If they can maintain the control affine structure of the manipulator equations, even if they're composed of lots of different components, it tries to make that available to you. Because it actually, in many previous modeling tools, it was really hard. Like as soon as you added a wing, you can't think of it as a multi-body system and you throw out all your best algorithms. Okay? But really the wing is just another force, and depending on how you model it, it can be very tractable and use the same tools. So that's the goal. Diagrams are awesome. They will make you powerful. They will go the distance. It's not a Drake thing. It's a control theory thing, right? The Drake thing is copy to vector, and I apologize. That's kind of gross, but it's because of good intentions. Any questions about that? I mean, people had questions on the thing about diagrams. Does that kind of at least tell you why it's there? There were a few, just like kind of tell us like what's the philosophy behind these things? So the kind of questions I had. So happy to answer any more like that, but maybe that's enough for now. Off soapbox. Good. Okay, so let's talk about acrobots, cart pulls, quadrotors, and actually there's a handful of other mechanical systems that you'll see. These are kind of the canonical underactuated systems. Actually, they've even leaked into the learning community, right? So if you look at, for instance, the OpenAI GYM, which is the sort of one of the original reinforcement learning benchmarks, you'll see little wiggling acrobots and cart pulls. Mountain cars, more of an RL thing than a controls thing, but it's still an underactuated canonical system, okay? And these are some of the classic benchmarks now for reinforcement learning, right? Similarly, if you go to the DeepMind control suite, which is maybe a slightly newer set of benchmarks in Mojoko, right? So you'll see the Acrobat, you see the simple pendulum, you'll see the cart pull. And then a bunch of other ones like ball in cup, right? Little half cheetah fish. Everybody needs the fish, right? These are the kind of canonical systems. Some of them are more like Reacher's not so underactuated in some sense, and some of them are much more complicated. But there are a handful of sort of canonical underactuated systems. You'll hear a few other names. Maybe if you come across them, they all fit sort of directly into this sort of playbook. There's one called the Penjubot. Oh, I have it written on a slide for a second. I don't have to write them down. So, okay, let's say what the Acrobot is. Okay, the Acrobot is a 2-link arm. I'll draw it out here. Okay. A 2-link arm, so that's like attached to the world. I've got 2 links. It's not a simple double pendulum. It has inertia along the link. Okay, so the inertia is distributed in this case, and then it has a motor here, but no motor at the shoulder, if you will. Only a motor at the elbow. Right. So it's called the Acrobot because it's a little bit like an acrobat on a high bar, where you think most of the work is done by the hips. You have a lot of strength in your core and not as much torque to give at the wrist. Okay, and like an acrobat, you can do things like swing up and balance at the top. That's kind of the canonical task. So this is a hardware Acrobot that we have it was in my office until very recently. But when you see in the lab, okay, so even though it's missing a motor, you can still swing up and balance much like Acrobat. And when we're going to do good optimization for this kind of thing, you can actually, really nail it with that's sort of good optimal control for swing up and balance of the Acrobot. Okay. Yeah, backlash is annoying, right? Yeah, yeah, and stiction actually is the other. But so okay, so if you're perfectly here and you're never exactly in the fixed point. If you're anywhere but the fixed point, you start falling. Okay, and you actually have to take its non-minimum phase. So you actually have to take some sort of a gross movement, but you have to sort of overcome your little bit of threshold because of the stiction and the backlash. That's actually an actuator that we worked hard to reduce any backlash and stiction. It's actually a belt drive that's carefully designed to sort of minimize that, but it's still tough. Yeah, you can do better thinking of it as a hybrid system, which we'll actually do, but backlash is kind of one of those things that there's really not a beautiful control answer for. It just kind of messes everything up. I also even have, so the dynamics, of course, are available in Drake. And so I've got notebooks that you can play with that will, of course, simulate the Acrobot. And if you want to have a good time, try to Teleop it. It's really freaking hard to get that up to the top. See, I'm using the arrow keys to swing it back and forth. It's like, imitation learning is not going to solve the Acrobot anytime soon, I don't think. At least not with my interfaces. It's really, really hard. I actually think, we spent a long time working on the Acrobot for a while. I actually think it's almost too hard. Like, I think focusing on the Acrobot for a long time, it's like too hard. Like, most of the problems in the world are not as hard as the Acrobot. It can distract you on the wrong issues. Okay, and then what's the cart pole is sort of the other canonical system here that we'll talk about first. You've seen this, I'm sure, before. Some people just call it an inverted pendulum, but I think of it as basically the double integrator where you have a force here, but we also have a simple pendulum attached. So you have a mass of the pole and a mass of the cart, frictionless ground. It's basically a double integrator with a pendulum on top. And the goal, again, is to swing up and balance the pendulum. So this one, I spent a little more time than I probably should have messing around with this before lecture. I made a joystick interface to give myself a chance at, all right, here we go, ready? I'm gonna do it. Oh, I'm out of sync, so let's try again. Oh no. Stage fright. Come on. Oh, I swear, there we go, there we go. Teleop's not the right way to do this in general, but that's balancing. I've got no chance. Okay, but it's kind of fun to try. Stop. Okay, but you get a sense for what the dynamics are, right? You have to push back and forth on the cart. There's a free joint, the pendulum, and you have to swing up and balance this thing, okay? A more elegant control solution looks something like this. This is, forget about the particular algorithm for now. This is a simple cart pull. Okay. That's like what optimal control does, as opposed to what Rust does badly with the joystick. And that's Philip, actually. So maybe it's not. It might have been Philip's undergrad, but. Okay, yeah, so what are these canonical underactuated systems? The things you might have heard besides this, quadrotors actually snap right into the same kind of class of machinery. Pendubot is a lot like the Acrobot, but you put the motor here instead of here. Ferruta pendulum, reaction wheel. Ferruta pendulum is similar, but you're now, one of them is spinning around this way, okay? But reaction wheel pendulums, convey cranes, ball and beam, even ball bots or segways, the simple control that you would do for that, are very similar to what the kind of things we're going to talk about for the Acrobot and the cart pull. They all have pretty similar strategies. So the equations of motion for these for all of those are going to take the form that I advocate for constantly. This can be a function of q also, plus b u, okay? Where for the Acrobot, let's just think about how this maps. So q is going to be the two angles, call it theta 1, theta 2, right? U is going to be the torque at the elbow, let's say. Okay. B is going to be 0 and 1, because your torque at the elbow directly actuates theta 2. Okay. And then typically you also have a torque limit, otherwise you can kind of cheat physics. If you have infinite bandwidth and infinite torque, then you can make it look like you're fully actuated. Okay, so unsurprisingly, it's underactuated, right? B is low rank. For this one, for the cart pull, we're going to say Q is the x position of the cart and the theta position of the pole. U is going to be the force on the cart. Okay. B is going to be 1, 0. And then we typically have, again, some sort of torque limit, force limit. And this one, if you noticed in the video, like, it's hard to make an infinite cart pull. So you also tend to have to think about state constraints, lest you bang into the side of the track, right? And the exact M, C, tau G are, I won't write down, but they're derived in the notes if you care. It's kind of funny, right? Like if you look at the code for the OpenAI Gym Acrobot example, they have like almost the right equations, and then there's actually a comment saying like, this doesn't look right, I don't really know what's going on here. So anyways, there's a right answer. There's two right answers, because that's why people get confused, because you can write the moment of inertia relative to the joint or relative to the center of mass, and that makes the equations look a little differently. So people are like, I see two different types of equations in the textbooks. One of them must be wrong. It's the same thing. It's just a matter of how you parameterized your inertia. OK. So the task is to swing up and balance, right? The one I did very bad, or I failed to do completely, actually. But we saw some success stories in the video. We've developed a few tools for dynamic programming. How are we going to do it? Right? Is it more like the tabular case? Is it more like the LQR case? Do we need something new? Right? So let's say the tabular case. Does that solve these problems? Right? We were talking on the way in. I said it works roughly up to 5, maybe 6 dimensions if you push it. And these are 4 state variables, right? So 2 positions and 2 velocities. So this is potentially in scope. And you absolutely can solve these problems with value iteration. But you will be surprised at how hard it is. It's like sort of disappointing. The amount of resolution that you need is very high in order to capture, especially like the same kind of stiction issues we were talking about, but even if you don't even model the stiction. The fine-grained detail that you need to get right at the top requires a lot of resolution in positions that are hard to guess a priori. Yeah? So if you can a priori say, I want resolution in a certain place, that'll get you somewhere, but it's even then surprisingly hard. And then there are algorithms that try to adaptively refine the mesh. They have their limits, though. So because what tends to happen is you have a suboptimal policy, so you start adding resolution where you don't actually need it, and then in the process of sweeping to the optimal policy, you kind of end up covering a lot of your space with dense meshes, and it's pretty inefficient. If you had the optimal answer and you ask what's the best place to do my mesh, then it's easy. But yeah, these can be done. It has been done, but it doesn't feel like the right answer. Like it just doesn't feel like, such a simple problem. We shouldn't have to like write highly optimized mesh codes. Gosh, I guess I need to like put a request into the room people saying, make the monitor not flash. We'll see. OK, so I really want to say yes, but it's not elegant. How about LQR? Right? LQR was for linear systems, right? And these systems are not linear. They're definitely not. The nonlinearity is somehow essential to the way they operate. So what good is LQR going to do? Yeah? That's beautiful. That's what we're going to do. Yeah, that's great. Yeah. So he says, what if you use 2 controllers? What if you do something maybe coarse to swing up and handle the nonlinear dynamics, right? And then LQR is going to be a beautiful solution at the top. But I want you to really understand that. I want to work through that and kind of understand that. So this is a beautiful solution at the top. Okay, so let's think about how we're going to apply LQR to the nonlinear system. And the obvious answer is we're going to linearize. But the mechanics of that and how effective that is, I think, is worth kind of going through. Because, I mean, I had the wrong impression. When I started my career, I was like, linear control is bad, nonlinear control is where it's at. And I was wrong. Linear control is actually awesome for a lot of problems. It doesn't solve everything, but it's highly effective in surprisingly nonlinear settings. Yeah. Okay. Well, we're going to see. I mean, even the simple pendulum had a sine theta sticking in the middle, right? That sine theta breaks everything. In the double pendulum, you're going to get more sine theta, cosine theta, sine theta 1 plus theta 2. That's where the nonlinearity comes from. Yep. They're directly from the gravity terms. If you think about the potential energy is like a cosine theta, and the gradient of the potential energy is a sine theta. Mm-hmm. Yeah, it's basically the effective gravity is opposite here as it is, opposite here as it is here, let's say. Easy one to see. So it doesn't change sort of smoothly, and you must reason about that. So let's think about how we do LQR for nonlinear systems. Okay, in the general form, I have a nonlinear system like this, right? LQR was for a particular form right, the linear state space equations. So what we need to do, what we are going to do is take a Taylor approximation of the nonlinear dynamics to make a linearization around some particular nominal operating point. Okay? So that's an operating point in both x and u. If you want to linearize these, you have to give a nominal x and a nominal u, all the arguments. So let's pick a linearization at the top. Okay, so x will be, let's say, theta for the first link and 0 for the second link. The second link is a relative angle. Okay, and then u will be all zeros at the upright. When you're actually at the top, you don't need to torque. Yeah. This is my choice, my cost function or whatever. My choice is to try to stabilize the upright configuration. So that's not a property of the system. That's just my problem specification. Yeah. Do you have to choose a fixed point? Yes. So, well, sorry. Today, yes. In 3 lectures, no. Yeah? Yeah. It's easier if you do yes. Yeah, a fixed point. So let's say, and you'll see why in a second here. Choose a nominal xu. We want it to be a fixed point. Okay. And then the mechanics are things you know. So I'm going to say that the x dot is approximately f evaluated at that nominal point plus the gradient of f with respect to the first argument evaluated at the nominal point times x minus x0 plus gradient with respect to the second argument evaluated okay. That's the first order Taylor approximation of that equation. You could say, you could keep going and do a second order approximation if you want, but the linear system approximation is the first order. You'll see people write this in 2 different ways. I wrote x dot is approximately this. Another thing people will write is x equals this plus higher order terms. hot. Two different, that's just your style choice. You can make that an equality, but then you have to admit there's some missing terms. Okay, so we're close to a linear form here, but we don't actually have it yet. This looks like an affine form because I've got kind of a linear, this is a matrix, right? Partial f, partial x. F is a vector function with respect to a vector argument. So this is going to become our A matrix, okay? This is going to become our B matrix. But I've got a bunch of extra terms here that it's not just x dot equals ax plus bu yet. To realize that, I have to change coordinates, okay? So I'm going to choose the error coordinates to be x minus x0. Okay. Now, if I take the derivative of that, I get x dot minus x0 dot, which, if x0 dot is non-zero, that's kind of a weird thing. I missed a dot here, sorry. The derivative of that. If x0 dot is not 0, then it's like your coordinate system is moving on you. It's not impossible, but it just changes the game a little bit. There's extra terms that you have to track. So it's much nicer when that's 0. Okay. But in general, this thing here is x0 dot. Okay. And then I'll also name u bar is u minus u0. So if I take this over to the left-hand side, then I can say that now I have x bar dot equals a x bar plus u bar. Okay, and that is actually a linear system. The affine term is taken away by operating in the error coordinates. Yeah.
Can you just expand one more time on x dot minus x dot not needing to be 0? So I can think of like for an aircraft, you linearize it around a trim point.
Yep.
So the velocity is constant.
Yep. That's a great example. So, so the language of trim conditions is slightly different than the language of stability. You can be stable to a trim, but that's different than being stable to a fixed point. It all goes through, but you have to carry around these extra terms and thinking about your movings. You have to make an argument about your coordinate system being invariant under those transformations. Like there's certain velocities that the equations are the same no matter what, the fact that you have some positive velocity. We talk about cyclic coordinates and stuff like that. It all goes through. But the simpler case is to not have that. Yeah. Okay, so apart from the slight detail of having to work in the error coordinates, we're basically just doing a vanilla Taylor approximation. Yeah. Yeah. So you're saying this one or this one? This one, right? So x0 dot is the dynamics evaluated at my fixed point, or at my nominal point. Use my words more precisely. So imagine I took a linearization here, but with 0 u. Okay, then the dynamics are moving me down right now. So the dynamics, if I were to say what is the dynamics here, it's going to say you're leaving. You have a gravity term that's pushing you away from the origin. Okay, and it's not impossible, but it's affine, not linear. It's my kid, and she called twice. So if she calls one more time, I'm going to answer. I think she knows I'm teaching. So, but I'll give it one more time. Okay. That broke my chain of thought. All right, so yes, so almost it's just a vanilla Taylor approximation, but we have to subtract out the error coordinates. The question is, how good is that Taylor approximation? Like for interesting nonlinear systems, like the sines and thetas sines and cosines are the things that break our linearization. Like how bad are sines and cosines, right? And sines or cosines are not, basically all the rigid body systems the nonlinearity enters through sines and cosines, basically. That's the natural operator. So let's think about it. Let's even draw it. Okay, so how about for the simple pendulum? That's the only one I can kind of draw on the board. Okay, I had ml squared theta double dot plus b theta dot plus mgl sine theta equals tau. Here x, so q is just theta, okay, which means x is theta dot, right? U is tau, all the same things, okay? We're going to linearize about theta equals pi, that's the upright. Theta dot equals 0, and u equals 0. That's sort of the analogy to the double pendulum version. These dynamics in state space form look like this, theta dot, and then 1 over ml squared tau minus b theta dot minus mgl sine theta. Okay, so quick sanity check. If I put in pi here, sine of pi is 0, theta dot is 0, I get, and tau is 0, so I get theta double dot is 0, right? So at this fixed point, x dot 0 is 0, it's a fixed point. And now what's the linearization of that look like? It's not hard to derive, but I'll just write it down so we can look at it. Okay. Okay, looks something like this. If I evaluate this at means cosine pi equals 1, then this thing becomes just 0 negative, sorry, it means equals minus 1, right? And I get g over L 1 negative b over ml squared. All right, so that's my A matrix. My B matrix here looks like this. Okay, easy. Now keep in mind, I apologized for this before, right? But there's a B in the linear systems form, and there's a B in the manipulator equations. I could not find a symbol that was to my liking that would separate those two, but they are different, right? I will never write them on the same board without a line over it or something like this, but this is the B in the linear systems form, right? It's the size of the state vector, not the size of the Q vector. Okay, now here's something I'm going to do over and over again in the class. These are not too scary, but they're still a little bit more than I want to deal with on the board. Okay, so I'm going to basically set mass equal to 1. Okay, I'm going to set length equal to 1. I'll set b equal to 0. I can't quite get myself to set g equal to 1. Okay, I'll set g equal to 10, and we'll deal with that, okay? So then the things we're operating here with are going to look like this, okay? And the question is that a good approximation of the pendulum dynamics around the top? Now, we did a little bit of this in the in the state space in the dynamics lecture, but let's do it a little bit more carefully here. So for a linear system, I know a lot of things, especially a two-dimensional linear system. I can do all my graphical analysis, and it's beautiful and it's good. The stability of linear systems is about the eigenvalues and eigenvectors of the A matrix, unsurprisingly. Okay, so I'll try to make that clear, but so let's just think about u equals 0 and just look at the dynamics of, remember we drew the pendulum dynamics. We drew it when u was 0, then we drew it for a couple different u's. So let's draw the u equals 0 case. And that'll be completely defined by the eigenvectors and eigenvalues of the A matrices, of the A matrix. All right, so you'll remember your eigenvalue definition, right? It's the thing that multiplying by A by an eigenvector gives me is the same as multiplying the eigenvector by a scalar. Right? And the thing we have to work with is the determinant of A minus this equals 0. That's the characteristic equation. And if you crank it through it, you'll see that this thing has two eigenvectors and eigenvalues. They look like 1 over square root of 10. Okay, lambda 2 is negative square root of 10. V2 is negative 1 square root of 10. Okay, so now if I draw my phase portrait, I have theta versus theta dot. Okay, I've got V1, which is something like this, right? Square root of 10 is like, I don't know, 3-ish. So it's like a slope of 3 kind of line there. This is my V1. V2 is just a negative of that. It looks like this. This is my V2. Sorry, why does that matter? So, okay, so the first thing to notice is that these vectors span the space, right? They form a basis of the space. What does that mean, right? So I could write any x as a linear combination of V1 plus V2, right? If I pick up any point in the state space, I could always write it in the coordinates of V1 plus V2. That's what it means to span the space. And then if I want to, the cool thing about this is that if I have, x dot equals ax, that's equivalent since this thing is additive, that's equivalent to lambda 1 alpha 1 V1 plus lambda 2 alpha 2 V2. In the eigenbasis, figuring out the derivatives is just looking at using the eigenvalues. So the implication of that is that when I'm on, for all the states that are on the eigenvectors, the dynamics are trivial, okay? They're gonna, it says that any vector here is going up with like a square root of 10, right? That's lambda 1 square root of 10. And any vector here is going down with lambda 2 equals negative square root of 10. Okay, I know it's a little bit, if you haven't seen it for a while, it's a little bit to remind yourself of, but that's what I'm seeing here first. But it's better than that, okay? Any point in here I can write as a linear combination of those. So let me get more colors going here. Okay, so if I pick this point, it's going to be mostly this one, right, and a little bit of this one. So it's going to look a little bit like this, okay? And it turns out, if I plot sort of the vector field around here, you're going to see these beautiful, okay, anywhere you look here, you're going to see sort of the interpolation of that linear vector field like this. That's what the linearization of the pendulum equations around the upright looks like in the error coordinates. that clear? Now here's the cool thing. You already knew, or let's see, the nonlinear dynamics. If I were to overlay the nonlinear dynamics that I already drew many times, the eyeball, right? The eyeball is like this, right? Is that clear? Even it's like this. The pendulum equations, the nonlinear equations, do that same thing. Okay? So the dynamics of the simple pendulum are nonlinear. But the linearization is an excellent approximation of them. Like, excellent. It gets these details right? An excellent approximation for a big portion of state space. Yeah? Yep, so at every one of them, I mean, I just, I did more than the computation in my head. I knew what it was going to be, right? But every one of them, I take a point. I would evaluate it as the sum of two of the components of the eigenvectors, okay? And I would take their those components with the eigenvalues. So that allows me to tell you exactly what the x dot needs to be as a simple linear combination of those two vectors. So as I span from here, let's say from here to here, I'm getting all of this one and none of this one. Here it's all of this one and none of this one, and it smoothly interpolates between. So it has to go from this vector to this vector. In the middle, it's exactly like this, and it smoothly sort of goes between. Just because I know that those things linearly interpolate. And similarly, you can do the same sort of argument. It's a little harder to think about, but you have to go from all of this one to all of this one, and it goes sort of smoothly in between. Yeah?
So the origin of the plot that you drew is
Yep, that's right. Yep. So normally, when we originally drew the pendulum, I put the origin here, but we're living in the error coordinates now, so it's shifted by pi. Okay, so like for, I don't know, big part of state space, it's actually a really good approximation. Now there's a place over here, okay, where the nonlinear dynamics is going down and the linear dynamics is going up, and it's a terrible approximation if you go far enough, right? But there's a big part of state space that it's really, really good. Yeah? Yep. Him first and then you, yeah? Okay, so when you're dealing with control, small errors can add up. That is possible, but feedback is a great remedy for that. So if we were just executing it open loop, it's true that we would depart from our orbits, but we're going to see that we can make things very stable. Yeah?
So you mentioned using controllers, nonlinear, and then you switch like WR. So, I think you're showing it's a reasonable linear approximation, but where can I draw theta dot dot?
Yep. We are going to give you very nice, very satisfying solutions to that problem. Okay, so to forecast it just a little, right? So we're going to look at so the linear controller also comes with a Lyapunov function, a candidate Lyapunov function for the linear system. That's also easy to get. And then you can ask, when is the Lyapunov function for the linear system also a Lyapunov function for the nonlinear system? And there will be a definitive boundary for that. And we're going to be able to compute it with pretty high accuracy once we understand Lyapunov everything. Yeah? Yes? I think for this, you could come up with thresholds, and it would probably work fine. I think the generic question is, how would you define those boundaries? It's going to get harder to tune in the harder systems. So having machinery that sort of does that formally we'll just go farther. Yeah, but in this, we could absolutely put a threshold. Yeah. Okay, awesome question. There's a lot underneath that. So the arguments roughly go like this. So if your linearization is stable, that implies that your nonlinear system is locally exponentially stable also. And that is also true of the closed loop system. So if you put a linear controller with a nonlinear system and you linearize the closed loop dynamics, then you can talk about stability of the closed loop system. And it is true that stability of the linearization, assuming everything's differentiable and everything, then the stability of the linearization implies stability of the nonlinear system. If the linear system is marginally stable, then you lose that guarantee. The marginally stable system in the linearization could be unstable, stable, you can't tell. It's just like, I don't know. But if you have a definitively stable linear system, then you are definitively stable, at least locally, you know. And then the Lyapunov type arguments that talk about how local. But I haven't really told you that yet. So that's just a foreshadowing. Yes? Yeah. What's that? Oh, good. Okay. Yeah. So I mean, basically, the eigenvalues of A have to be negative in order for the system to be stable. The original pendulum is actually unstable without a controller at the top. If you were to linearize around the bottom, you would get 2 negative eigenvalues, and it would be stable. Our goal will be to find a linear controller, LQR controller, that makes those both negative. And that will change the vector field, so everything's pointing towards the origin. The condition on the eigenvalues in continuous time is simple. It's just less than 0. Left half poles is the classic feedback way to say that. Yeah, and then if it's a discrete time system, you have to be less than 1. That's the inside the unit circle condition. Good. Okay, so like I'm going to show you way more complicated examples later in the course of like perching aircraft that are in post-stall. You know, remember that quick video? But like the linearization is surprisingly good, like through post-stall aerodynamics along a trajectory. It's not just because this is like too simple of a problem. Locally, you know, these dynamical systems are very nicely described by their linearization. Okay, so let's do a little bit more. So remember, I lost my white chalk. Sava, remind me to recharge my white chalk. It's like writing with my fingernails. Okay, so we can do LQR design, right? To try to find the stabilizing controller. We have our x bar dot equals a x bar plus b u bar. So we have our systems. We're going to try to minimize a cost function, which is going to be an infinite horizon x transpose qx u bar transpose ru dt. Okay, and you can just call basically QR, okay? Or you can actually, if you just take the system, in Drake you could also call a linear quadratic regulator system QNR, okay? And it'll do the right thing, it'll give you a system back. And the thing it gives you back, remember, is u equals negative kx, right? Which was this negative R inverse B transpose. We were trying to talk through that thing, right? Which was this is like partial j partial x. This was then transforming that into the actions you can actually take. And if you'll remember, what it gave us was this x, also j star was x transpose bar sx, okay? And that s for the pendulum gives us a cost to go function that looks like this. That is sort of elongated along the dynamics of the pendulum. That was supposed to be symmetric around this point. It's a little bit bad artwork there, but I think you get the important point is that it's elongated this way, right? It's the cost of being along this vector, which is pushing you away, goes up faster than if you're along this vector, which is already bringing you back towards the origin. And LQR discovers that beautifully. And I want to just take a second to appreciate how awesome that is, okay? So I can take basically so I take my A and B matrix, okay? There's a condition that those A and B matrices have to satisfy. The system has to be stabilizable. If it's impossible to stabilize the origin, then LQR will say, can't do it, which is nice. It doesn't just fail mysteriously, it says, fail, clearly says your system's not stabilizable, try again, okay? But for any choice of Q and R had to be positive or non-negative. Q can be non-negative and Q and R had to be positive, okay? But that's not a hard thing to pick, right? Any choice you make of Q and R, you're going to get a K out and an S out, which makes the closed loop system stable. Okay? In particular, the system A minus BK x, that's what you get from having u equals negative kx inserted into x dot equals ax plus bu, right? I just stick that in, I get A minus BKX. The eigenvalues of this are going to be negative for any choice of Q and R. Actually, there's an interesting point which we'll make on the next problem set, and we'll get back to actually in probably the next lecture, but you can add a discount factor in here. That's a standard thing to do in RL, to have a discounted long-term reward, which makes a lot of things better, and we'll see why. If you add a discount factor here, though, that breaks the claim I just said. You could if you have a discount factor, you could choose a Q and R and get a K that is not stabilizing. Okay, that's just chew on that. We'll come back to that, but it's kind of, yeah. Adding a discount factor is like being overly optimistic about your dynamics. It's like pretending your dynamics is more stable than they actually are, and you can trick yourself. Okay, now the reason that's so cool is that if you're in a complicated system and you were just searching around in K, let's just say I was going to like put K on or do RL or something like this, right? If I'm just going to like search around by changing numbers in K, run my simulation, change my number in K, then there are a lot of Ks that are unstable. And in fact, defining the boundary of what is a stable K or not, it's an eigenvalue problem. It's possible, but it's a kind of a subtle boundary. It's not like just the positive orthant. Okay? So searching directly in K is kind of hard. Searching in Q and R is easy, and calling LQR is relatively easy. Some people say, oh, you just shifted the problem, and now you have to pick Q and R. Oh, but that's way better. Like, that's way, way better. You can pick any Q and R, pretty much, and it's going to give you something good. Dialing in your performance exactly, maybe you have to think a little bit more about what Q and R should be, okay? But it's almost always good. By the way, I could tell you what Q and R should be roughly. From for the pendulum, I recommend that, okay? And for the double pendulum and R, it can be just 1. Okay? For the double pendulum, I would recommend that. So we can think about that, right? So if I increased both Q and R, if I just multiplied this and this by 2, then that would just be a multiple of my cost. That wouldn't change my optimal controller. Okay, so if I move both Q and R up and down, up together, then that doesn't matter. What matters is the Q versus the R. How much do you care about getting to the origin versus using too much effort? Okay, so there's a scaling there that you just don't have to worry about. Just pick R to be 1 if there's the only thing, and then figure out, just mess with Q. Now, why do I say this? Okay, it's like really, almost every LQR controller I write is roughly as that cost function. It's really not like I'm spending a lot of time dialing in Q and R. This is almost the identity matrix. The only thing is that Q, right, if it's X transpose QX, the units of Q are in radians squared, if you will. This is like radians squared. Okay, the units of this one are like radians per second squared. So you just need to change units to make them similar. Okay, so what's the right change of units between radians per second and radians? I don't know. So square root of G over L, like if I have a pendulum that's roughly a meter long in a gravity that's roughly 10, then square root of G over L is square root of 10 squared, because I get a thing, that's 10. Okay, so if your robot's a meter tall, then this is a great scaling. And all my robots are, a meter. Well, they're not a millimeter, right? They're like closer to a meter than any other thing. So I just kind of use that as a rule of thumb. And when I see this in a cost function, I see that as basically the identity function, but just normalized for units. Just like having a characteristic time constant that goes from radians per second to radians. Did I say that clearly? I didn't write anything, so if I need to say that more carefully, I can. Yep. A lot of things change. You mean like my ability to tune cost functions specifically? There's a finite horizon linear quadratic regulator method in Drake and in some other packages, right? That does the general form of that. You get A as a function of t, B as a function of t, Q as a function of t, and these can be trajectories, okay? And you can hand in a final cost, an extra, final horizon, final time cost. It's going to be very similar, and you'll get back a K of t and an S of t if you did all that, okay? But a lot of the machinery will extend, and that's what's going to, in our moving coordinate systems, if we're linearizing around a trajectory instead of around a point, we get to this kind of a formulation. Yeah?
Are there like a star kind of method or some sort of optimization method to find the absolute minimum time to do this, bring it to the origin, or minimum control? Like, I know Q and R sort of are related to those two things.
Right.
But are there methods to find the actual Q and R that say minimize time for minimum?
Yep. It's less beautiful than you might think. There is a minimum time LQR problem if you want. You can choose if you want to keep this or if you want to put a U, a bounded U. Most of them involve a line search in time. You can, for any time, you can solve the problem optimally, and then time is just a scalar, so you can just kind of walk up and down until you find the right time. It tends to come in a nonlinear way. You don't get to solve that in one shot. GCS can do it most of the time, the graph of convex sets thing, but But classically, it's a line search. It's super cool, actually, that you can kind of look as you start changing the knobs on this, like on Q and R. You can say, what does K do? For instance, let's even leave that alone. Let's just start cranking up R. Okay? You can imagine as I turn up R, the cost on U, that's going to make K smaller. Okay? But it won't let K go to 0. Like I actually plotted this for myself. Let me just draw it here. I plotted this for myself just to get a sense for what it actually does. And it, as you change R up and you ask what are the values of K, K is going to be 2 numbers. It's a gain on position and a gain on velocity. Okay, because U equals negative Kx, that's like negative K1 theta minus K2 theta dot, right? So I guess I should make those lowercase because they're scalars now. Okay, so what happens is these things, K1 sort of goes down and asymptotes, and this is K1, and K2 goes down and asymptotes on another thing. It won't let you go to 0. It has to return stabilizing controllers. It's like guardrails that are saying, you can put in any Q and R, you can ask for me to do like, that I hate spending any energy, okay, and it'll still stop you from making an unstable controller. It's a very elegant way. There's actually even a better way to parameterize. So, okay, if you here, so if you think about, we kind of talked about 2 different parameterizations of the controller. You could parameterize K directly. The space is a little complicated. Okay, you can parameterize Q and R. This parameterization is easy. Just pick something positive, and you always get a stabilizing controller. But there are stabilizing controllers that exist which cannot be gotten from LQR by changing Q and R. Right? So it parameterizes only stabilizing controllers, but it doesn't parameterize all stabilizing controllers. There's one more parameterization that it's written up in the notes. I don't know if we'll get to in lectures or not, called the Euler parameterization that parameterizes in a convex way all stabilizing controllers. So that's even better, yeah? But LQR is pretty darn good, and it's super easy to compute and everything, yeah?
Unstable or not stable.
Okay, so that's a good question. So do the eigenvalues go, as I crank up R, do the eigenvalues get close to 0 so that if I were to like have model errors, would that get sensitive? I don't actually know the answer to that. I think that's, I'll look at that for this system specifically. Yeah, no. So I think if you crank up R, my intuition is if you crank up R very, very high, say really try not to use any energy, and it'll put it closer to the boundary of stability, then you're going to be more sensitive to model errors, right? That's not like a common problem. This is like an extreme asymptotic argument we're talking about. But I think you're probably right. I think that is probably on the boundary of stability. I would guess if I plotted the eigenvalues of this as I went to R goes to infinity, that it's probably going to 0. But I don't know that for sure. I'll check that. Great question, yeah. Okay. There's another important idea here. So what have we said so far? We said LQR actually works pretty well for nonlinear systems. I tried to convince you that looks really messy in retrospect, but I think as it was built up, hopefully it made sense, that the linearization is good over a big swath. LQR figures that out sort of beautifully, and it's a nice parameterization. It always gives you stabilized controllers. There's a relationship as we're in this sort of linear analysis world there's other things that you might know from linear control theory that are sort of important in the discussion. If I give you an x dot, or this linearization, there's a notion of, is that linearization controllable or not? There's also a notion of, is it stabilizable or not? Okay, so is the pair AB controllable? And then there's a related question, is the pair AB stabilizable? Okay, I'm going to make sure you understand what that means in a second. So one big takeaway here is that you can be underactuated, but still controllable. Okay, that's a super important. I mean, that's kind of like everything we're doing here. Underactuation is talking about instantaneously can I produce accelerations. Controllable, as I'm about to define here, is talking about could I get to the origin, let's say, could I get to a new point in state space if I'm given time to get there? And those are different questions, right? Underactuated says you have to think harder about your dynamics, but the Acrobat, for instance, you can get up to the origin, you can stabilize the origin. The linearization around the top is underactuated, but it is controllable. Okay, so what does controllable mean? Controllable means given some x at time 0, some u trajectory that's going to be defined over a finite window, t0, t final, can I find some u such that x at time t final is 0? And you're allowed to pick u and you're allowed to pick t final. Is it possible to find a trajectory of actions that will drive me to the origin in a finite amount of time? All that matters is tf is finite. It doesn't have to be 10. It just can't be infinite. Does there exist a set of commands I could send that would drive me to the origin? The nonlinear extension of this would be you'd have to go from any initial condition to any final condition. In the linear, just going to the origin is sufficient. That means you could go to anywhere. Okay? Does that make sense? The Acrobat, there is trajectories which in a finite time can drive me to where I want to go, even though instantaneously I can't take arbitrary trajectories. It's underactuated. Stabilizable is actually, for linear systems, is a strictly weaker condition than controllable. Okay? It just says, given an x0, find me a u of t defined for t0 to infinity, okay? It doesn't have to be finite time, such that the limit as t goes to infinity of x t is 0. The difference between controllable and stabilizable is that you're allowed to take infinite time to get there in stabilizable. Okay? It turns out that's an important difference because, in fact, LQR only needs you to be stabilizable. It doesn't need you to be controllable. Here's an example. Okay, a system that is stable and has no control inputs is stabilizable, but it is not controllable. Did I say that right? Yeah, if the system has no control inputs, you have no control authority, but it's already stable, then the limit as t goes to infinity, x will go to the origin. So basically the difference here is that in stabilizability, if there are some states that are uncontrollable, as long as they're passively stable, then that's enough. Whereas controllability requires that you can get there in finite time. That means you must have control of all of your state variables, because a linear system cannot arrive in finite time to the origin. Yeah.
So maybe practically this finite time will be so long that it becomes
That's true. That's true. Yep, there's always, so oftentimes people talk about controllability as a Boolean thing, but really the rank of the controllability matrix is, the rank is binary, okay, or it's an integer, but the condition number of that would tell you like how controllable you are, and that's probably more relevant in practice. I completely agree with that. Okay, I got to try one thing here just to make that point here. Haha! I promised this was coming. Okay. I don't care if you get the right answer, okay? But I want to see if this works. So there's a simple question there, which I can open up on the screen too, if that helps. I guess I can't while you're taking pictures, but I will in a second. Of a simple A-B pair. And I want you to think for a minute about whether it's controllable or stabilizable. And there's a bunch of things that may not work about this. Like, I hope everybody has a Google account. All right, did that work? Roughly? I thought I could just click on it. Okay, I guess I can't open it easily. What's the answer? Yeah. Right. There's a stable thing that you couldn't control, right? And then you can control the second variable, but you have to rely on stability in the first variable. All right, I'm basically done. Let me just show you, because it's just fun, right? So you can take that basic recipe, and you can just take all of our canonical underactuated systems. You can take the cart pole, you can linearize around the top, 10, 10, 1, 1. You get a beautiful stabilizing controller out. Okay, you could take the Acrobot. You can linearize around the top. You get a beautiful stabilizing controller out. I made big perturbations. Yeah, that was too big. Okay, because I wanted to show that, but I wish it hadn't happened the second random initial condition, but there you go. Okay, but you can even more than that. You can take Quadrotor. Restart. You can take a planar Quadrotor. You can call LQR. You can call LQR. Did I press? Oh, he was waiting for me to choose my Python interpreter. And then you can wait for it to generate the animation. I'll come back to that in a second. Okay, and the last one, you can take a 3D Quadrotor. And you can just 10, 10, 1, 1 roughly, and you'll get a beautiful stabilizing controller as soon as it wakes up. Yeah. It's not even an extension. Well, I didn't install something new for Simple Browser. It was there based on whatever extensions I already had. Yeah. Yeah, it's good. I bet it is downloading every model in Drake because I updated something. Damn it. Anyways, there's a Skydio Quadrotor that's about to come up and be beautifully stable. Let me see to this. Okay, and this is the planar Quadrotor. All these things just kind of work. Oh, there we go. See, look at this. That's see now side by side. That's pretty darn good. Okay. The Skydio founders are MIT students, so I asked them if I could use their artwork in class, and they said yes. So that's awesome.